We've been talking a little bit for a while now about this curvilinear motion and some of the different components you can use to solve these problems. And most of the problems that we're going to run into, you're going to be able to solve using those rectangular components with the XYZ, or you'll be able to do with your normal and tangential components. Those are usually going to be our best ones. But on occasion, we may have some where cylindrical and polar coordinates are going to be a good option. And we're not going to use it a ton in this class, so this is just going to be like a brief overview with an example of how we use these cylindrical components and when we might want to use them. So again, our curvilinear motion, if you're moving along some line, curvilinear motion, if you have something that is described by a radius and coordinate angle, right? So if you have something that is given by r, the radius vector, as well as an angle, right? So r and theta as a way to describe the position of this particle, wherever it is as it moves along in its curvilinear motion. This is when you would want to use polar coordinates or cylindrical coordinates. Really, your big tip-off on these is going to be the angular velocity or angular acceleration. If you ever see these terms, angular velocity or angular acceleration, that's a really big tip-off that we want to use polar coordinates. Acceleration, that's an aeration. Angular acceleration. So you're usually given things in terms of r's and thetas. You may be given some kind of angular velocity, angular acceleration. That's when we would want to use these polar coordinates. So what is this, right? What are our position, velocity, acceleration when we're talking about this? Our position, again, as we just wrote, is usually given in terms of r and theta, usually in relationship to each other. So it's not using any x's or y's generally. It's only using these r's and thetas. So when we find our velocity being the derivative of these functions, right? Velocity derivative of position, we're actually going to have two components to our velocity now. We're going to have a velocity with respect to r, with respect to that radial coordinate, and then a velocity associated with theta, associated with that transverse coordinate, that angular coordinate, where VR is going to be our derivative of r with respect to time. You may also see that written as r dot. Whereas the theta, our transverse coordinate, is going to be just the radius times the derivative of theta with respect to time. And this guy right here, this theta dot, this is the angular velocity. D theta d time, that is angular velocity, and that's your really big tip-off to use these equations. Okay, so that's r d theta over dt. Which means we're going to have one other relationship here, our acceleration, and that's going to be the derivative of our velocities. When I take my derivative of my acceleration in the radial direction, I'm going to have the second derivative of radius times radius, or minus radius times theta dot squared. Right, and where these come from are they're from chain rule derivatives, where you have both r and theta are variables. So that's why we're having multiple components inside of these. We can also write this is d squared r over dt squared. So that's the second derivative. Remember, the dot is just derivative with respect to time. Minus r times that theta with the dot over it, again, angular velocity. D theta dt, and d theta dt is squared. And then we can also have the theta component of this. So much like our normal and tangential had an n-axis and a t-axis, this is similar in that we have this r and theta, these r and theta axes, so to speak, where a theta is going to be r times the second derivative of theta plus 2 r dot theta dot. Or if you don't like dot notation, as I am not a big fan of dot notation, it's the second derivative of theta with respect to time plus 2 times dr dt times d theta dt. Where this theta double dot, that's our angular acceleration. Put these over there. So when we have those angular velocity, angular acceleration, it's a really big tip-off to use some combination of these equations. And usually you're given some kind of r equation or some kind of theta equation, some combination of them that we just take derivatives of, plug values into, and then solve for whatever acceleration or velocity components that we're likely interested in. Again, with these, the magnitude works exactly the same as we've seen in all of our other forms of this curvilinear motion, all of our other forms of magnitude of velocity and magnitude of acceleration. And that's going to be that our magnitude of velocity is just going to be the square root of VR squared plus theta squared. And for acceleration, it's the square root of acceleration in the r direction plus acceleration theta squared. Alright, so those magnitudes still stay the same. It's still square root of the squares when we're finding these magnitudes of velocity and acceleration. Again, we're not going to work with these polar coordinates a ton. This is just to show it to you so that you know it exists in case it ever comes back up, especially later in your schooling career. You may see it in other engineering courses. Just to be aware that this exists, and this is another way that we can set up and solve these curvilinear motion problems. And so with that, we'll take a look at just one example here. So in this example, we've got a rotating platform that is rotating about the vertical axis the vertical axis such that at any instant its angular position, see there's our angular or keyword, angular position, and then it gives us a theta. A pretty big tip off, we're going to want to use polar coordinates. Our angular position theta is, and this is a little hard to read, but it says theta is 4t to the 1.5 power in radians, where t is in seconds. The ball rolls outwards along the radial groove so that its position is r equals 0.1 t cubed. I'm going to write that down too. Our r is 0.1 t cubed. Determine the magnitudes of velocity and acceleration of the ball when t is 1.5 seconds. So I want to find velocity and acceleration at t equals 1.5 seconds. So again, we're given some theta in terms of time, some r in terms of time. Really going to tell us that we're going to have to use these polar coordinates. They're just going to make the most sense. It's going to be extremely difficult if you try to convert it to x and y's or normals and tangent. It would just be a mess. So in this case, use what they give you. Go ahead and we're going to do this in the cylindrical coordinates, finding those magnitudes of velocity and acceleration. So to do that, right, what are those equations? We just went through those equations for velocity and acceleration. We said that magnitude of velocity is our square root of the r component of velocity squared plus the theta component of velocity squared. And our acceleration is the square root of the r component of acceleration squared plus the theta component of acceleration squared. Right, so we have those guys. And does that help us much? Not really. We still need to know what we need to grab. What is this VR? What is V theta? What is AR? What is A theta? So our VR, and we can go ahead and substitute this in there. We said our VR is going to be the derivative of r with respect to time. It's going to be that dr dt, or r dot, or r prime of t. Any of those, however you want to think about it. Plus our v theta. And our v theta, we said, is the r d theta dt. And that whole term is squared. Right, so we can do it this way, or we can just work to find those components of acceleration. So we could also just find AR, which we said equals the second derivative of r dt minus r d theta dt, and that term is squared. A theta is going to be r e squared theta dt squared, second derivative of our theta. And then we have plus 2r theta, nope, 2dr d theta, sorry, these are derivatives. I had them in dot notation in my notes. Okay, the dots are too easy to miss. This is why I don't like the dots. dr dt, d theta dt. So clearly, we're gonna have to find a lot of derivatives. There's no way around it. There's just a lot of derivatives to be plugged in here. So let's go ahead and just evaluate all of these. Go through, find all of these derivatives of theta, find all these derivatives of r, plug in those t's so that we could find all of the stuff that we need to be putting in here. All right, we'll go ahead and we'll do these thetas. So theta equals 4t to the 1.5. I can go ahead and plug in my 1.5 for t in there. Nothing stopping me from doing that. 4 times 1.5 to the 1.5 power is going to give me my theta value of 3.75, right? Just plugging that into the calculator of 4 times 1.5 to the 1.5. That's all that is, just plugging that in. Because I want those actual values. I'm finding these velocities and accelerations at t equals 1.5, so I might as well just go ahead and plug them in. You can do it while you're taking derivatives, or you can take all your derivatives first. You can do it in whatever process you want. I'll do it both ways. Let's do thetas where we plug them in each time. We'll do r's where we do derivatives first. So thetas, we plugged in our t, we got a theta. Let's take our derivative of theta with respect to t. So 4 times 1.5, 6 t, and then we minus 1, so that's going to be 0.5, 6t to the 0.5 power. If I plug in 1.5 in there, 6 times 1.5 to the half power. That is also, very interestingly, going to give me 7.35. Also gives me 7.35. That's very interesting for our d theta dt. And then finally, we'll take a second derivative of my theta equation, d squared theta dt squared. So that is my 6t to the 0.5 that we're taking the derivative of. So if I bring the half down, I get 3t and then minus 1. It's going to give me negative 0.5. I get 3t to the negative 0.5. If I plug in my 1.5 seconds there to the power of negative 0.05. And I'm going to get my second derivative of the theta function is about 2.45. So we are going to rinse and repeat, do the exact same thing with our radius. That radius equation, 0.1 t cubed. Radius equals 0.1 t cubed. And this time I'll go through, take all my derivatives first. So derivative of r with respect to time is going to be 0.3 t squared. Take another derivative. I don't actually know if I even need this derivative, but I'm going to take it anyways. d squared r over dt squared, second derivative, r double prime, r with 2 dots over it, whatever floats your boat, is 0.6 times t. So now I can plug in that t equals 1.5 in for all of these, and I'm going to get r is 0. I have 375. dr dt, if I plug in the 1.5 for t, is 0.675. And d squared r dt squared, our second derivative, plug in 1.5 for t, gives me 0.9. So now I have all these values. The values are really what I care about. The values are what are going to get plugged into all of those fun equations up there. All these thetas and all these r's that we found. We'll find our velocity first. We said velocity. Here's our velocity equation. I'm not going to write this guy again. We're just going to start plugging things in. So our velocity is the square root of dr dt squared. So where's our dr dt? Here he is. 0.675 squared. Plus r times d theta dt squared. So where do I have? I have r over here. I have d theta dt right here. So plus 0.3375 times, do a big bracket, times 7.35. Those times each other, and then those both get squared. They're all under the square root. That's just something we pop entirely into the calculator, and we get a velocity of 2.57 meters per second for our velocity. Okay, last one, I promise, we're almost done. We're going to find this guy. We're going to find our acceleration, which has these two very lovely, extremely monstrous components to them. And I don't think I even have any room to stick these all in the same equation. Gosh, by gosh, we can sure try. Or not, I really don't have room to be writing all this out. So if I find my, gosh, I don't even know how to write this. I'm really gonna run out of room. Let's put it, you just overwrite it. Just overwrite it. We don't need this velocity anymore. A big, long, disgusting acceleration equation up here. Alright, so my acceleration equals the square root. It's going to be a big one because we've got the AR squared and the A theta squared. So our AR squared, boop, 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 we're going to put in our big AR squared, is going to be second derivative of R. Found that guy? Here he is. He's 0.9. 0.9 minus R times d theta dt squared. So R, here he is, 0.3375. 0.3375 times d theta is 7.35 squared. That entire term squared. Plus, that wasn't that bad. Now we can do our acceleration theta direction. Might be a little worse. Plus, our radius r, we have that. That's our the big brackets again, 0.3375 times second derivative of theta times 2.45 plus 2 times dr d theta. 2 times dr, that dr is 0.675. 2 times 0.675 times theta, again 7.35. All of that is squared, and everything, absolutely everything, gets captured under that square root. It's going to be a huge pain to enter into the calculator, several places to mess up, so be very careful when entering it. And double check me, tell me in the comments or in class if I'm wrong, because I'm getting an acceleration with this of 20.4 meters per second squared. And I could be wrong, I make mistakes all the time. I'm a person too. And this is a lot to type into a calculator. But this is how we use these polar coordinates when we're given these angular velocity, angular acceleration, position. If you see angular, it's a big clue. If you see the thetas, that's a huge clue that you're going to be using these polar or cylindrical coordinates. Otherwise, just try to assess the problem on what really would be the easiest way to analyze it. Does it give you a velocity in the tangential direction? Does it give you relationships of x and y that would be easier to work in an xyz coordinate system? All of these types of things, you're going to have to first pick the best coordinate system for you, and then understand those position, velocity, acceleration relationships in that coordinate system, even though they're always derivatives of each other. Understanding how they work in that coordinate system so that you can solve these problems.